Hello everyone. In the previous class, we had the discussion on classification systems for rock masses. So, today we will learn few aspects related to failure criteria for rocks. When I say rocks means first we will discuss about the intact rocks and then we will see about the rock masses. So, before we go ahead and learn about various failure criteria for rocks, first let us understand about the in situ stresses and conditions like plane stress condition, plane strain condition and axisymmetric condition, and then we will see that how the failure criterion such as Mohr failure criterion, Mohr-Coulomb failure criterion, how they work for rocks. So, as far as in situ stresses and strength they are concerned, it is extremely important for us to have the idea. So, in this course we will also learn about how to get or how to determine these stresses by conducting tests in the field. However, for the time being, please try to understand that what exactly do we mean by in situ stresses and strength here. So, it is evaluated exactly in the similar manner as it is done in case of the soils. So, basically these are the overburden stresses within the rock mass. Say for example, that if you consider the unit weight of rocks as 27 kilonewton per meter cube for the computation of overburden stresses. So, here you can see that there are various points on this plot. These points corresponds to some of the test data with reference to in situ stresses. These belong to the countries such as Australia, Canada, US, Norway or Sweden, then South Africa and some other countries. So, all the data when it was plotted on the same space, which is vertical normal stress on x axis and on y axis it is the depth. Then we could see that one can form a straight line such as sigma v, which is in megapascal, that is equal to 0.027 times z. So, that means that the variation of the in situ stress is linear. So, these tests were conducted all along various depths and that was varying up to 2500 meter, and it was seen that the vertical normal stress varied linearly with depth, which is represented by this straight line. So, basically this overburden pressure is equal to gamma times z in case if we took this as 27 kilonewton per meter cube as the unit weight of the rock. So, as far as rocks are concerned, sometimes horizontal stresses can be larger than the vertical stress, which is very rare in case of soils. So, in addition to in situ stresses within rock mass, stresses are also induced by tectonic activities, erosion and other geological factors. So, because of these, your horizontal stress can become more than vertical stress in case of rocks, and therefore K naught, which is the coefficient of lateral earth pressure, is greater than 1 and it can be as high as 3 at shallow depths. So, when I say shallow depths means most of the civil engineering works are being carried out at this depth only. So, you see that the reason that sigma v is much less than sigma h, in many cases you can have the value of K naught to be quite high. Then there is wide variability and hence the horizontal stresses should not be estimated. So, see on this plot, various data points are there. Again, these are from the countries such as Australia, Canada, US, Norway or Sweden, South Africa and others. So, when they plotted all this data on K naught versus depth space, you can see that the complete data can be confined between two bounds. Okay, so this is what is the lower bound and this is the upper bound. So these two dotted lines, they show the two bounds in which all the data points they were found to lie. So here the equation for the lower bound can be given by 0.3 plus 100 upon z, that is in meter. We need to be careful about the units when we deal with empirical correlations. Similarly, for the upper bound, the equation which was derived was k naught equal to 0.5 plus 1500 by depth in meter. Then later on, few research workers they pursued this study further, and some of these they incorporated the horizontal deformation modulus in this particular manner, which is represented by this expression, and they tried to obtain the coefficient of lateral earth pressure using this expression, which is also a function of horizontal deformation modulus. Coming to the stress strain relationship, so when we say that stress strain relationship, we typically mean by the constitutive relationship or the constitutive model. Common constitutive model which are used include linear elastic, non-linear elastic, elastoplastic, rigid plastic, strain hardening as well as strain softening, then Mohr-Coulomb, you have Drucker-Prager, then you have viscoelastic, viscoplastic, and the list is long. So basically these constitutive relationships, they tell us that how these strains are related to stresses. Let us try to take a look corresponding to various ways that stresses are related to strains. So the simplest analysis of a rock mass would be by considering it as a linear isotropic and elastic material, which is following Hooke's law. So we will have the modulus of elasticity, and you see that in general 3-dimensional situation how the strains epsilon x, epsilon y and epsilon z, they are related to the stresses sigma x, sigma y and sigma z, along with the elastic property of the rock, that is E, which is the modulus of elasticity, and nu, that is the Poisson's ratio. Similarly, shear strains, they are related to shear stresses and the shear modulus, which is G. Then the volumetric strain can be given by epsilon x plus epsilon y plus epsilon z, and you can write it in this particular manner in terms of the bulk modulus. So where shear modulus and bulk modulus, they can also be represented with reference to or in terms of the modulus of elasticity and the Poisson's ratio in this manner. Coming to the other condition like plane strain loading case. So the structures such as retaining walls, embankment and strip footing, where the loading is of the strip type, they are long in one direction. So the deformation or the strain in the longer direction can be neglected. So such type of situation, they fall under the category of plane strain loading. So for a plane strain loading, the strains they are limited to xy plane. So the stresses, that is sigma x, sigma y and tau xy, they can be represented in terms of strain in this particular manner. So, here I have written these three equations in the form of the matrix or matrix representation. So, here you can see that sigma x can be written as this particular term E by 1 plus nu 1 minus 2 mu into 1 minus mu into epsilon x plus nu into epsilon y. So, likewise you can represent sigma y as well as tau xy in terms of the corresponding stresses. Coming to the other type of loading, that is plane stress loading. This is not very common in most of the geotechnical engineering applications, and the example of such type of loading include a thin plate being loaded along its plane, and in this case stresses are confined to xy plane and stresses and strains they are related by this equation. So, you see that this is a bit different than the plane strain loading. So, as far as we as geotechnical engineers we are concerned, we mostly have a plane strain type of situation than plane stress situation. Coming to the next type of loading, which is the axisymmetric loading. This is quite common in case of the geotechnical engineering, including soil mechanics and also rock mechanics and rock engineering. So, an example of such type of loading may be that along the vertical center line of a uniformly loaded circular loading. So, it will have the same lateral stresses in all the directions. So, let us say if you take a look in plans, say this is the circular loading, say some uniformly distributed load is there and this is the center line. So, if we take any point in the soil mass or the rock mass, then such type of problem can be considered as axisymmetric problems. So, in these cases you will have the same lateral stresses in all the directions, and sigma 1 and sigma 3, these are called as axial and the radial normal stresses respectively, and these are related to normal strains in the same directions, that is epsilon 1 and epsilon 3 respectively, using this equation. So, basically here we have the r comma theta as the coordinate system rather than x comma y. Now, coming to the some aspects related to rock failure criteria, before I go to any particular failure criterion, let us try to understand that what exactly is the mechanics behind the failure of the rock. So, the confining pressure has significant influence on the failure pattern of the rocks. So, most of the rocks they are significantly strengthened by the confinement. As we have already discussed earlier, that when we increase the confining pressure, what happens is the behavior of the same rock gets transition from brittle phase to the ductile phase. Okay. So, most of the rocks, it has been seen that the strength increases when the specimen is tested at high confining pressure, and this is very significant, especially in case of highly fissured rock. Now, just imagine a highly fissured rock as a mosaic of perfectly matching pieces, as it has been shown in this particular figure. So, you see that each and every piece is matching perfectly with the neighboring pieces. You see? Similarly, if you just take this piece, see how nicely it is matching with neighboring pieces. Okay. So, we imagine the originally fissured rock as if that it is a mosaic of perfectly matching pieces. Now, how the deformation will take place, how the failure is going to be there, let us take a look. That for this rock to fail, there has to be some dilation, there has to be some displacement, deformation along the rupture surface. So, for that to happen, or sliding along the fissures to happen, the rock has to be free to displace normal to the average surface of rupture. So, let us say that this is the average surface of rupture. Maybe I can go to the previous figure, and let us say that here this is the average rupture surface. Now, the failure will take place only when there is the sliding normal to average surface of rupture, which is shown here. That see, this dotted line was the original portion, and here this is what is the locus of faulting that has been shown here. Now, what will happen if you have large confining pressure? See, when the confining pressure is large, the rock has to exert lot of energy in order to slide along these fissures, and therefore, the result is going to be more strength. So, under the confinement, the normal displacement which is required to move along such a jagged rupture path, it requires additional energy input, which is not uncommon for a fissured rock to achieve an increase in strength by 10 times the amount of a small increment in mean stress. So, let us say that I increase the confining pressure by a very small amount, and as a result the strength can go up by maybe to the tune of 10 times. And that is the reason why the rock bolts are extremely effective in strengthening the tunnels in weathered rocks. So, please understand, when there is this rupture path, when the confining pressure is more, the rock has to exert additional energy to have the normal displacement which is required to move along such rupture path, and this results into the increase in its strength. So, you see here that here the various stress strain relationship has been shown under different values of confining pressure. So, you see here this is P1 which is less than P2, this is less than P3, and P3 is less than P4. And please note down these 3 points A, B and C, and I will explain that why I ask you to focus on these points. So, what happens that when we increase this mean pressure, there is the rapid decline in load carrying capacity after the peak load. It becomes gradually less striking until you have a mean pressure which is known as brittle to ductile transition pressure. See, what I mean by this is, when you have the low value of mean stress or the confining pressure, see, after the peak load there is a sudden drop here. But then when the confining pressure is increased, that is P2. So, you see here this was the peak, and see here the slope was so steep, but here it became bit gradual. Further increase the value of P3, and beyond the peak, see, this is gradually reducing, and then you have the peak situation here, and it is not the reducing, but it is more or less becoming a kind of a ductile material. So, here there is, this is brittle, and here this is ductile. So, slowly in between this there is one pressure that is called as brittle to ductile transition pressure, and after this pressure the rock starts behaving as a fully plastic material. So, you see it is the same rock which was behaving as a brittle material at low values of confining pressure, but starts behaving as a ductile material at high values of confining pressure. Now, I mentioned to you that you need to take a note of those 3 points A, B and C. So, you see the failure pattern at those points, how it is changing with increase in the confining pressure. So, here the confining pressure was P1 which was less than P2, and in this case it was P4. So, you can notice that how the failure mode is changed when you are increasing the confining pressure. So, if you examine these deformed rock, that will show you that there is intracrystalline twin gliding, intercrystal slip and the rupture. So, the question is what should be the brittle to ductile transition pressure, how to get that. So, various research workers, they conducted so many studies, and in 1965 Mogi came out with the relationship that at brittle to ductile transition, the difference between the major and the minor principal stress, that becomes approximately equal to 3.4 times the minor principal stress, and later on when few other research workers, they carried out similar type of study. So, they came out with this relationship that sigma 1 to be equal to 3 to 5 times sigma 3. Now, with this background, let us start our discussion on some of the failure criterion. So, one of the first and the most basic one is Mohr's failure theory. Many a times we confuse between Mohr's failure theory and Mohr-Coulomb failure criterion. These are two different things. So, first let us understand what was Mohr's failure theory, and then we will learn about Mohr-Coulomb failure criterion. So, in Mohr's failure theory, it assumes that failure of the material that can be represented by a fundamental relationship between the shear stress that is acting on the plane of failure and the normal stress which is acting across that plane, such that it can be written in this particular form, that tau as the function of sigma n. Tau is the shear stress and sigma n is the normal stress that is acting across that plane. Now, the normal stress, whether it is compressive or tensile, that contributes towards the failure. And another thing which was assumed, that the material was not equally strong in tension as well as compression. In this case, the effect of intermediate principal stress, that is sigma 2, was ignored, and it was said that the fundamental relationship between shear and the normal stress is a typical characteristic of the material concerned, and this can be determined by conducting the tests in the lab or maybe in the field. So, accordingly, if there are two different materials, they may have two different functional relationship between tau and sigma n, although both may be said to follow the Mohr failure theory, but then this relationship is a typical characteristic corresponding to a particular material. Now, with this background, let us come to the failure criterion, that is Mohr-Coulomb failure criterion, most commonly used in the geotechnical engineering. It works quite well for various geomaterials, especially for soils where the failure generally takes place in shear. So, the shear strength on the failure plane tau f is related to the normal stress sigma. See, up to this much it is the Mohr's failure theory only, that is tau is equal to some function of sigma n. So, what Mohr-Coulomb did, that they defined this functional relationship as this expression, that is tau f equal to c plus sigma tan phi, where c is defined as a cohesion and phi be the friction angle. This is you must have used n number of times during your studies with respect to soil mechanics or foundation engineering. Now, the state of stress is represented in the space tau versus sigma and with the help of more circles. So, here you can see that I have drawn 3 more circles. One is corresponding to uniaxial compression test, and therefore, you can see that its sigma 1 is equal to the UCS of the rock, and sigma 3, that is the minor principal stress, is equal to 0 because it is uniaxial compression test. Then the second circle, it corresponds to the indirect tensile test, and we have discussed this. If you have conducted the Brazilian test, that is one of the indirect tensile tests. So, in that case you get the major principal stress as 3 times sigma t, which is the tensile strength of the intact rock, and the minor principal stress, take a note here that it is negative, that is equal to the tensile strength of the rock. You remember I mentioned to you that tension we will represent by a negative sign, and in case if you have a direct tensile test, that is uniaxial tensile test. So, in that case your major principal stress is going to be equal to 0 because it is uniaxial tensile test, and the minor one is going to be minus sigma t, that will be equal to the tensile strength of the material. So, what we do is in case of the rocks, there is the tensile strength which is available. However, in case of soils, there is no tensile strength. So, in order to represent that, what is done is that the Mohr-Coulomb failure criterion, this was extrapolated onto this side. Okay. So, that means that it is extrapolated in the tensile region when you have the minor principal stresses to be less than 0, as you can see that this circle and this circle. For that, these two circles, minor principal stresses, they are less than 0. Now, this I have already explained you that we have 3 more circles, one for the UCS, one for Brazilian test, and another one for the uniaxial tensile strength test. The assumption which is involved here is that the tensile strength that you obtain from the Brazilian test and from the direct test or the uniaxial tensile test, that has been assumed to be same. So, you can see that that is why both the circles, they have minor principal stress as minus sigma t. Now, if we see the actual envelope in the tensile region, it is going to be this curved portion which is shown by the dotted line here, but then we go ahead with the simplified Mohr-Coulomb extrapolation. So, you just extend this tau f, which is equal to c plus sigma tan phi, to the tensile zone, and then you provide a tension cutoff here corresponding to the value of sigma 3 as minus sigma t. So, when we simplify this Mohr-Coulomb criterion, when we apply this, what happens is we kind of overestimate the strength in the tensile region. You see, at any point the actual one is lower than the simplified one. So, we need to use the lower values of C and sigma t. So, these has to be used judiciously, and that is the reason that the left hand side of the Mohr-Coulomb envelope, that is in the tensile zone, is always worrisome. So, we need to use our engineering judgment if we are using this extrapolation of the Mohr-Coulomb failure criterion in the tensile zone. So, how do we represent it with reference to the mathematical expression? So, you can see that here this sigma c is there. So, that can be represented as 2c tan of 45 plus phi by 2, or you can also write it as sigma c as 2c square root of 1 plus sin phi upon 1 minus sin phi. And at the failure, the sigma 1 can be related to sigma 3 by this particular expression, where this sigma c can be represented by this expression. In case if you want to know more details about such failure criterion, maybe you can refer to these two links where I have discussed these failure criterion with respect to rocks in more detailed manner. So, what we learned today was about the in situ stresses, then plane stress, plane strain and axisymmetric loading condition, what is the effect of confining pressure on the strength characteristic of rock. Then we learnt about Mohr's failure theory and Mohr-Coulomb failure criterion. So, in the next class we will learn about some of the empirical failure criterion that we apply in case of rocks as well as rock masses. Thank you very much.